So let's introduce the Lyapunov's method for proving stability of a nonlinear system. Of course, you can use it also for linear systems, but there are easier methods of assessing whether a linear system is stable. For example, the Hurwitz criterion. But for nonlinear systems, this one has been proven to be quite robust and easy to use. Well, relatively easy. That depends on what kind of system you are dealing with. Let's start with a very simple one. Let's say that I would like to prove for today that a following system is stable. I will place on a horizontal plane a little card. Okay, then I will add friction to it. So when it moves, there is a little bit of friction on the wheels. Then I will add, okay, maybe a very particular friction coefficient. Then I will add controls to my system. I am able to control whether it is moving left, right, and the force that is pushing it. Okay, let's introduce the mass for the system. And that's pretty much it. I'm set. I can now create a dynamical model for this one. I will use Newton's method. So the second law of dynamics. If the system is about to move, I know that mass times acceleration is the sum of all the forces in my system. Okay, there is acceleration in here and there is none in here. So I need a second picture with a description of positions, velocities, accelerations, because these are missing. Let's assume that this is an axis that has a 0 here, and I am currently standing in a position x1. Then I am moving in this direction with a velocity x2, so the acceleration is the first derivative of velocity. Good. So this is actually x2 with a dot. Velocity with a dot makes acceleration. How many forces are currently acting on my system? Yet another picture, this time with forces. If I am moving with a velocity in this direction and standing in here, I am sure that something is stopping me from going too fast. So I've got friction. It will decrease my speed over time if I'm doing nothing. So I actually have friction minus F times usually V, so in this case minus F times x2. I also have a direct force acting in here. Now let's take a look in here. This is 0, this is the positive side. As you can see, I'm usually using always positive values when it comes to position and velocity, because this makes it easier for seeing in which direction does the friction act and inputs. Input is helping me, friction is stopping me. So friction is stopping me, input is helping me, plus minus. Okay, I've got my first equation. I also need to correct this is x2. Okay, this is m times x2. So my dynamics are, I will divide by mass, F divided by mass times velocity, 1 divided by mass, u. Of course, my mass was 1, my friction is 1. This is the equation for dynamics of my system. Of course, I need the full set of equations. So if I've got x1 as position, x2 as velocity, in order to get the full state space equations for my system, I need a set of both derivatives. The change of position is, by definition, the first derivative of position is velocity. The change of velocity is acceleration. And now I will test something. I would like to control my little cart, my little robot moving, and I will try out whether I can make it return to 0. My robot is here. I would like to test the stability of a control system. I'm introducing a very simple control system. If you have a position, for example, 5, the control is minus this position. So if I am standing here, my controls will be here. I will be trying to drive this direction. If I am ever to fall on the left side of my coordinate system at -2, my controls would be -2, so 2. Okay, is it stable to move like that? My new dynamical system, together with controls, would be, now this is a version with u substituted, x2 minus x2 minus x1. It's linear. There is no sinus, cosinus, there are no higher powers. That means this is a linear system. You can use Hurwitz criterion to calculate the eigenvalues of the state matrix. But I would like to test it using Lyapunov's method. What does it mean? Lyapunov's method is actually pretty easy. It is an assessment of how the system actually moves. So first of all, I would need to visualize the method. The method is based on the energy of the system. For a moment, let's assume that my system is like that. You may remember it from the faceplane portraits. It's a little wally where there is a ball that starts at the edge of the wally. What would happen in that wally? If you have gravity, it will fall here and then stabilize itself at the bottom. Okay, what does it mean? It starts with an energy on the side of my wally. So it starts, this is a big hole basically, but if this is the bottom, I am here at the height. So I've got an energy, a potential energy due to gravity, mgh. Now, if I will be moving, in a moment, I will gain a second energy. I will get a velocity, so I will get mv squared divided by 2 at the cost of my potential energy, because they will change one into another. If I've got friction, I will lose energy due to friction. So I will have heat transfer to the external side or to the air, if the air is very dense. So I will be losing energy due to this. But is it enough to stabilize my ball at the bottom? Okay, let's try drawing these two energies. If I am at the beginning, in this point, this means I have a total energy. Let's introduce a total energy, V. This is EP and EK. So both those two energies form a total energy. I start with a value like that. This is my V. Okay, but I have friction in this system and no external inputs. There is no energy flowing into the system, only outwards. So I will be constantly losing energy. If I start here, I will be moving down with the total energy. And when I actually move into the middle, I will stop moving, so there will be no kinetic energy, and I will be at the ground level, so I will have no potential energy. So at the very end, I should reach 0, and the ball cannot go any lower or gain negative velocity. So, okay, not negative velocity, the square, so negative kinetic energy. So I cannot go any lower. I can only stop at 0 and stick to 0 energy for the infinite time in this scenario. So I start somewhere, and in this case I start higher than 0, with an energy higher than 0. This is the ground level, and I have chosen it so that I start above the ground only. And then, after some time, I reach my stability point, my equilibrium point, and at this very precise point, the ball is lying flat on the ground, so the potential energy is 0. And I assume I am only losing energy. So the change of energy over time this is time, if you forgot, the change over time should be lower than 0. I should be going down, so the derivative should be negative. And when I hit the stability point, it should just stop. The ball should not drop lower, so even lose more energy. It should just stop, so this also should be 0 later on, after hitting the stability point. Those 4 conditions are the conditions necessary to create an energy-like function for the system. So actually, if I find a function like that for a system, and I prove that it behaves in this exact way, this means that the system is stable. Because it only loses energy, nothing else. Good, but this is abstract, without any equation for the system. What about my little robot, my little card, standing on a horizontal plane? My little robot is here. It has a dynamical model like this. Yes, I have substituted the u for minus x1. And I need to introduce for this model total energy of the system. Okay, I will assume that the only thing there can be in this system is, well, first of all, a kind of a kinetic energy, mv squared by 2, because it's moving. Yeah, but I wish for this system to return to 0. So I want this system to go back and then stabilize at 0. Hey, what kind of systems do this kind of movement? Spring-based systems. When you have a spring and you just move a system like that, for example, to a lower position, and you release it, it goes like this. When you have a pendulum, it also goes like this. So this is in general a spring-based system. What is a spring-based energy? If you have a coefficient for the spring k, what is the energy? You know the force is minus kx, but the energy? Kx squared divided by 2. So I can introduce here a spring-based energy, because I can see the system which has to return to 0, because I want it to return to 0. But is it true? I just took them basically out of a hat. I just told myself that, hey, the system is moving, let's give it a kinetic energy. Hey, it wishes to return to 0, let's give it a potential energy due to existence of a spring. But it's a virtual spring, there is no spring in here. So, will it work? That's the basic part of the Lyapunov's method. You propose an energy-like function and then you test it. If it passes our test, it will prove that the system is stable. If it fails, it proves nothing, you just chose a wrong function. So it's a one-way street. Now, what are my criteria? Do you remember a little plot from a second before? These are my criteria. You need to introduce a system that has a positive energy, so that when you actually land at the energy equal to 0, then you are sure that this is a stability point. And of course, this is just how the energy looks like. Is it true for this one? Do I have a mass for this system somewhere in here? I had before, but that was at the modeling stage. In here, I can't see any mass. Let's assume that the mass is 1. Do I have k? There is no spring. Let's assume that the k is 1. What is the velocity of this system? x2 squared by 2. What is the position of this system? x1 squared by 2. Okay, I have modified my energy-like function because I lacked a couple of parameters and I substituted the correct variable for example, velocity. Now, let's check. Do I meet this criteria? These two. First criterion is it's bigger than 0. always. Except for this point, but is it? Well, x squared is always positive. X squared is always positive. Yeah, that's bigger than 0. If I substitute 0, is it perfectly 0? Let's test it. 0 square, 0 square. Yes, it's 0. Passed. Okay. What about the falling part? It needs to be falling, and then it needs to stop. Okay, let's test the falling. What about the derivative? This was, after substitution, x2 square, x1 square. So what's the derivative of x2 square by 2? Of course, it's 2x2 by 2. That's the derivative. But what about the fact that I'm taking a derivative with regards to time, and this is x. Oh, I need the inner derivative, so I need x2 with a dot afterwards. Okay, what about this one? Again, x1 squared by 2. 2x1. Okay, divided by 2. And inner derivative, because this is a function of time. Good. So I can simplify it a little bit, and I'm left with the derivative of my energy, so how fast is it falling or rising, if I failed the choice for my Lyapunov function, is x2 times x2 with a dot, x1 and x1 with a dot. And this is the stage where you introduce your system. So far, we have worked basically without this knowledge. We had just a picture of our robot. Where is it going? So it wishes to go here. It's moving with a speed, and due to only these two informations, we introduced kinetic energy and potential due to the existence of a spring or spring-like movement. Now it is time to join it with the actual dynamical model, because this is my model. There are two derivatives here and two derivatives here. Let's use this knowledge. x2 times x2 with a dot. Minus x2 minus x1. x1, x2. Okay. I will lower the brackets now. This is minus x2 square minus x1 x2 plus x1 x2. Oh, those two simplify. I am left only with minus x2 square. The question is this always lower than 0? Well, yeah, there is a square, so this is positive, with a single minus sign in front, so this is always negative. And is it for 0, 0? Minus 0 square? Yep, it's 0. But this is only for x2. I will need an additional theorem later on to prove this, that this actually works for both of them. But basically, it's always negative. So, yeah, I have proven that my system is returning to 0. Why? Because I have chosen an energy-like function for my system. This was this part. And then I have proven that those 4 requirements are met. I have tested whether it's bigger than 0. There are 2 squares. Yes, it is. I have tested whether at 0 it is 0. And then I have tested the derivatives. If all 4 are met, this means that this function actually behaves like an energy function for the system. And since it behaves like one, and energy is always falling and going down to 0, this means there is a stability point and it is 0.